click something else. Okay, so we're recording now. So we've got a basic example of u sub, and we just finished talking about how cosine, sine, tangent, all of our trig, all of our like natural log and exponential functions, it's kind of easy to see what is going inside these functions. And it's a dead giveaway, is there a function nested inside of one of those? And then it's kind of the first thing your mind wants to go to when you check these u subs. So we kind of check that, let's use green to do our highlights today, that this guy here is nested on the inside. And if we kind of think of head, it's something like x to the fourth. And so if we have an x to the fourth polynomial, when I take its derivative, we get x cubed. And so the derivative also appears outside here. So we can make our u substitution x to the fourth plus 2. That'll be our u. And then my derivative is going to be 4x cubed dx. So I'm going to do this one a little bit different than some of the ones we were doing yesterday. This is a different technique that a lot of students like. I do want to just tell you to be a little careful with this in terms of just how we manipulate the differentials. And this will kind of just exemplify a little bit more of why these constants don't quite matter. It's really this function and the differential. We have this x cubed dx in the problem, and that's what we have in this differential substitution. So what you can do is solve for dx. So dx is just going to be du divided by 4x cubed. And fair warning, whenever you do it this way, it's only multiplication and division with these differentials. Whatever these terms that are being attached, these functions that are being multiplied by the differentials, you have to multiply and divide to the other side. You don't want to add and subtract. If you start adding and subtracting when the differentials are involved, you're going to run into problems. So this gives us a pretty easy substitution now when I rewrite the problem. We can keep this x cubed. We've got a cosine, and now this inside part we said was just u. And then this dx, we can just rewrite by this statement this substitution statement that we just solved for. So this du divided by 4x cubed. And when you do it this way, you got to look out for, because now what's going on, I mentioned this yesterday, that we don't want different variables involved. This du that we have here now dictates what variables we need. We need everything in terms of u, but I still got these x's in here. So we have to make sure that all of these x's cancel. And this is kind of the thing you got to be careful about if you like to solve these types of problems this way. It is kind of, it's easier in some sense because you can just solve straight up for dx and then make that substitution in here. The extra algebra, the extra work now comes in this step. And you do have to just look out for this x cubed divided by that 4x cubed. So I can write out that step a little bit more. It's all multiplication, so we can kind of shuffle things around. It's just x cubed divided by 4x cubed cosine of u du. And then the x cubes cancel. So no more x's. It's exactly what we want. And really all we have now is this 1/4, which I'm going to pull outside the integral. And it's just cosine of u du. You guys still see that? And then we just go ahead and do the integral. So we've got 1/4 sine u plus a constant. And then we back substitute 1/4 sine of x to the fourth plus 2 plus our constant. Okay, so next one we want to take a look at. Let's do, some of these can get a little trickier. So let's do some of these trickier ones like tangent. So if we want to integrate tangents, there it's kind of misleading, right? Normally with these u subs, we want to look for some sort of nested functions and then their derivative, but there's no nested functions here. It's just tangent. And so sometimes these u subs they play roles in other situations beyond this kind of nested function. And really what we want to do with this one is think of tangent as sine of x over cosine of x dx. And now you kind of have to think a little extra hard to see what this function is nested as, because it's just a quotient. So the nice thing about sine and cosine is that they are derivatives of each other, right? Derivative of sine is cosine, derivative of cosine is sine with a minus sign. And so that should work out pretty nicely for these u subs. The thing we just want to be careful about is we always need the derivative in the numerator, because we want this sine x dx to be the differential, to be the derivative of whatever other of the function that we want to make our substitution for. So our cosine of x here is going to be our natural choice for our u sub. So let's check that. If I make u is equal to cosine of x, then du is sine of x dx. And I'm just going to go ahead and substitute that in. So cosine of x was my u. And then now we always think of these differentials, if there is a fraction, think of the differentials as sitting in the numerator, just like you would of multiplying a fraction out front by a constant or something. We really consider it as in the numerator. So it's sine of x dx in the numerator. Our sine of x dx substitutes as du. So you can either write your du in the numerator there if you want, that's fine. The other way that it's commonly written is just going to be 1 over u and then keep our du's after the integral. So write the same thing there.
It's going to be negative sine of x for du.
Sorry, what'd you say? Yes, negative sign. Thank you. Yeah, forgot my negative. So we need negative there for all those. And you can pull that negative sign out of the integral if you want. And so the integral, what do we get? We get negative natural log. For natural logs, we want to keep these absolute values there, especially since the domain wasn't originally specified. We assume that it is both positive and negative values, so we need the absolute value. We need our plus c, and then we just need to back substitute natural log of absolute value of cosine plus a constant. Okay, another example. Let's see. Let's take a look at some of these square root ones. Can be a little tricky. So that was tangent. Let's take a look. The other ones that commonly come into play ultimately end up being linear substitutions. So let's take a look at this guy, 3 minus 2x. So x times square root of 3 minus 2x dx. So what can our substitution be here? This one's a little tricky. And we always throw this in some sort of problem, either on a homework, quiz. Problems like this often come up because they're a little awkward. They're a little different than some of these other problems where we've just done, where we've kind of naturally seen a substitution and its derivative. Because in this case, well, I have a square root, but this x out front isn't the derivative of the inside, right? The nested function here is the square root of 3 minus 2x, but the derivative isn't x, right? This is a single power of x. When I take the derivative, I just get a constant. If this were x squared, then it would kind of work out that this is my nested function and that is the derivative. So it's a little strange because we don't see a derivative of the nested function. Easily, at least. So, well, what's going to happen? The trick is to look for a linear substitution. And it's not that the statement, it's not entirely correct. It's not that we don't see the derivative. It's that we don't see it easily. Like, the derivative is there because what happens? Let's take a look. When I say linear substitution, I simply mean y equals mx plus b, right? It's a linear function. And in this case, we're using u. So u equals mx plus b. So our first guess was, well, this nested function under the square root 3 minus 2x is the nested function. And that is really what's screwing up this integral, right? If this were just square root of x and it were some polynomial out front being multiplied, I could just turn square root of x into x to the 1/2 and then distribute. We wouldn't even need a u substitution for that. But I can't integrate a square root of some complicated expression while still being multiplied by x. I can't do that easily. But we make a linear substitution, and that would have been my original guess. And the nice thing about linear substitution is, what is the derivative of a linear function? It's just a constant. And as I was mentioning yesterday, constants aren't a big deal in these differential substitutions. So while there's no x, I can still make a substitution for this dx. And so we've made a little bit of progress, but let's see what happens. So this just means, let's go ahead and write it as dx is negative 1/2 times du. And if we tried to make this substitution, what happens to my integral? My integral becomes, well, I still got this x hanging out front. We've got a square root of u. That's not too bad. Square root of u is much more easily integrable than a square root of some more complicated expression. And then what happens to my dx? My dx becomes negative 1/2 du, and that is multiplied. So all in all, rewriting it, we've got a negative 1/2 out front times the integral of x squared of u du. And did that help us? So what's our problem, right? I've got this du here. We've got these x's hanging out. I need everything in terms of u. So the question remains is how to get rid of the x. Can you guys still see that? Am I writing on the page? Looks like it. Yeah. And the answer is to manipulate the original substitution. This commonly appears with linear substitutions because linear substitutions are easy to manipulate back and forth between u's and x's. It can be used with other substitutions as well. It just gets a little more complicated. So it may not be a trick you want to try at first. You might want to try some of the other tricks in terms of looking for u subs or possibly different techniques of integration, which we'll learn our second one just shortly. Okay, so manipulate the original substitution. What do I mean by that? Well, we just made a nice, easy linear substitution. U is 3 minus 2x, but that also implies that I can solve this guy for x. So if I solved it for x, we're going to have u minus 3, and then
Could you bring your
divide.
paper up?
Yeah, actually, let me see. I think that's getting in the way. Let me move that up. Is that better?
Yeah, thank you.
Yep. So we're solving for x, so I subtract the 3 over, divide by -2, and that is my x. And so since I solved for x, and again, this is just u's, I can now plug that back in to the original equation. So we've got our x's is now, I'm going to write it as -1/2 times u minus 3 times square root of u du, and then we got to remember this constant out front. We had another -1/2 out front. So all in all, let's simplify everything first. Sorry, that's a positive 1/4 now. And we've got u minus 3 times square root of u du. So quite a few steps there. This is one of the trickier u subs, because we had to do this extra step of solving for x, but now it looks a bit nicer. The square root doesn't have anything complicated underneath it. It's the linear part, or the more complicated polynomial, is now outside of the square root. And now what we can do is just distribute and integrate. So we've got 1/4 times u times square root of u, which I'm going to write as u to the 3/2, right? This is just u to the 1/2 times u to the 1 minus 3 u to the 1/2 du. And now we can integrate. We've got our 1/4 times 2/5 u to the 5/2 minus, we will have 3 times 2/3 u to the 3/2. All of that plus a constant. So my powers, I'm just raising u to the 3/2, add 1 becomes 5/2, u to the 1/2, add 1 becomes 3/2, and then I like to just multiply by the reciprocal of those for my constants. And of course that 3 is still hanging out. Let's go ahead and simplify. So we've got 1/4 times 2/5 is going to give me 1/10 u to the 5/2. I've got, these two 3's are going to cancel, and then I've got 1/4 times that 2. So it'll give me a 1/2 u to the 3/2 plus a c.
The paper up again.
Yeah, let me move that. Better?
Yeah, that's good.
And then our last step is just to make the substitution. So I am running out a little bit of paper here, but I think we'll be able to fit it in. So we've got 1/10. My u is now 3 minus 2x to the 5/2 minus 1/2 3 minus 2x to the 3/2, and then plus a c. Any questions on that guy? Okay, so just another thing to look out for. If it looks like it could be used with a u sub, sometimes it is like this linear substitution, and then you've just got to do this fancy trick to get rid of the extra x's once you've made your substitution. Okay, any questions on u subs in general? So those two examples, I didn't do any evaluations. I hope that's fairly clear from the examples we did. Again, the key part is making these substitutions and being able to compute the antiderivatives. Plugging in the values, I want to leave that challenge to you guys. It's not much more. Just remember that if you convert to use, then you either need to change the bounds of integration in terms of u, or do the problems like we were just doing, back substitute for all your x's, and then plug in the original x values. So let's talk about integration by parts. Integration by parts is the product rule in reverse. So what does the product rule say? The product rule says that if I want to take a derivative of a product of two functions, then we get this. That we have the derivative of f times g is f prime times g plus f times g prime. So naturally, of course, if I integrate both sides, that just says that f of x times g of x, so this is just applying an integral to both sides, is equal to the integral of f prime of x g of x plus f of x g prime of x dx. And so because we can distribute an integral over a sum, sorry, I forgot my dx for that one. We get a statement that looks like this. And how are we going to manipulate it? Well, we're just going to subtract one of these guys over. So we're going to have it as f of x times g of x minus the integral of f prime of x g of x dx is equal to the integral of f of x g prime of x dx. So what is this saying? If I want to do an integral, so in an integration problem, we're usually given a statement like this. So this is why I wanted to solve for just one of these integrals. And just like with u sub, we just want to look for a way of manipulating a given integral to look like a more nicer integral, something that I can solve, something that I can find an antiderivative of. And so what is this saying? This is saying, well, we're looking for a product of two functions. But unlike u sub, the product is two completely different functions. This g prime of x dx, it's the derivative of some function, but it might be a function that's not even related to the other function in the product. Whereas with these u subs, we were kind of looking at this nested function, and then its derivative was being multiplied on the outside. If you don't have that situation, it's likely that we're in an integration by parts technique that we want to use. that I'm looking for, well, I have a product of two functions, and more importantly, we have one function that is integrable, or at least one function that we can find its antiderivative of, and then one function to take a derivative. Does everyone see that? Let's rewrite this statement a little differently. So another common way that we see integration by parts, just as a general rule, you commonly see it as the integral of u dv is equal to u times v minus the integral of v du. What does this mean? So this means that we have a product